All right, so got 2 emails this morning about questions. First one about the discussion board, then one about the homework. So this is all organic. We'll talk about the discussion board this week, which is looking to take this alcohol and convert it to 2 different products. One is this bromo complex. The other is this trans bromo complex. And the question got asked, do I have the right? So what I see is a thought process of doing the elimination and doing the addition back with bromine. So the person who sent me this, you are correct. The second step is going to be the bromine addition, and the tip off here is the fact that you're given this trans symmetry with these molecules. So good in picking that up. Now, the question I got to ask is, yeah, I'm trying to figure out what's going on with, maybe I forgot to schedule a day. But that's more of a problem for like probably later today, me to figure out what's going on with YouTube. My guess is I just forgot to schedule a day, and this is like kind of just, I'm off by 1 day. So we'll see. I can easily schedule another one for Thursday, and but what I do is I have to go through and figure out what's going on with the YouTube links as well. So there's a process involved with this, and there's got a lot going on right now because we are getting ready for the next semester. But anyway, back to the question I got asked was, okay, how do I know when to use solvents? How do I know when to, when are solvents important? Why do you need them? Well, good question to ask here, because what you see is that one of these is an E1 mechanism, the other is an E2. So whatever we're doing in the first step here, this is an E1 mechanism and this is an E2 mechanism. Because what will happen here for the E2 mechanism is that we'll get elimination between this carbon and this carbon, so no carbocation rearrangement. And you're going to want to do this under basic conditions. And this is really where you want to specify the solvent as something like, I think THF. One of those low dielectric constant solvents, because you want to make sure you don't get carbocation rearrangement. So you would specify the solvent if you expect the solvent to have implications in terms of your mechanism. Now for this BR2, there isn't any implication. It's the solvent doesn't play a role. It doesn't do anything to stabilize the intermediate. Now with this one, for the root 2, I would definitely say that this is a better situation where you do H2SO4 and water, not the terp-butoxide, because the terp-butoxide is a big bulky base, but you are typically going to run into conditions where, well, you really want to favor the E2 mechanism here. And the best way to do that is with a polar protic salt, polar protic high dielectric constant solvent like water. So if you do acid catalyzed dehydration, that'll give you the E1 mechanism. But as far as when to choose when you use solvents, particularly with E1, E2, SN1, SN2, that's when it's going to matter, because you're controlling the bimolecular or unimolecular pathway by your solvent. Your solvent plays a major role. So you specify it when it plays a role, you don't specify it when it doesn't. All right. The big one. All right, questions 15, 16, 19, 20, 21, 22, 24, 25, 26, 27, 34, 39, and 40 on the McGraw-Hill homework. So let's start with 15. And if you got questions, please feel free to post them in the chat. Otherwise, I'm just going to start working through these. So identify the alkene obtained by the dehydration of 2,3,3-trimethyl-2-butanol. Better marker than this. So we have 2,3,3-trimethyl-2-butanol. And dehydration. So when it comes to this, our dehydration is going to come off of this carbon. So even if we go through like an E2 pathway, there's nothing to rearrange to. It basically, if you move a methyl group, nothing's going to happen. It's just the same thing flipped. So the only option here is do elimination off the end. And so in this case, we still got the butene. 1, 2, 3, 4. So this would be 2, 3, 3, trimethyl, 1, butene. So let's see if I'm right. Yep. So elimination here, you have to have a hydrogen to eliminate off of, so you can't do this because this gives you 1, 2, 3, 4, 5 bonds around carbon. Carbon doesn't do that for organic molecules. So our only option here is to eliminate it off of one of the methyl groups. All right, question 16. The following alcohol has been subject to acid catalyzed dehydration and yields a mixture of two isomeric alkenes. Draw the two alkenes. The major and minor product is predicted by Zaitsev's rule. So we've got 2, 3 OH bound to this one here. And we're looking for the major and minor products. If we do elimination, the major product is going to follow Zaitsev's rule. We have a hydrogen here, so when we form this carbocation for elimination, this is the most likely one. That said, you will isolate a trace amount of the non-Zaitsev product, which is the alkene going up. So the major product will be the 2,3 dimethyl 2-butene. And the minor product here is going to be your 2,3,1-butene. 2,3-dimethyl 1-butene. All right, next question. 19. Predict the product of the following reaction. We have methoxide in DMSO and heat. So this is actually a good question. I wonder how they approach it. So you got a few options here. With methoxide, this is a small base. It's also an alcohol. And so we have the potential for carbocation rearrangement. We have the potential for elimination with the potential for substitution. So your strong base here, we're going to use some context here. We know we're under a, we know we're in the alkenes unit. Odds are we're forming the alkene. So let's try this as a first pass approximation. So you've got the 1, 2, 3, 4, 5, 2-pentene. Another option is carbocation rearrangement. So let's say because we are in DMSO, this forms a carbocation. We can get a tertiary carbocation like this, and we would get elimination between the two. So my first guess is this, that it's going to just do a straight E to elimination. Let's see if I'm right. So it seems to think that's right. What we're doing with this is just a straight elimination. So we're going to assume no rearrangement. This isn't unreasonable for an alkyl halide. The chloride popping off, forming a Cl- carbocation, that's not as likely to happen as something like an alcohol. All right, so the next question is, how is it eliminated? And it asks you which of these is going to happen. So is HA or HB removed, or does it not matter? When we're doing this through an E2 pathway, and we know it's E2 because we didn't get that rearrangement here, it has to be anti-periplanar. So HA has to be the one that gets removed because it is anti-periplanar. And that's it for that one. So with the E2 mechanism, they just have to be on opposite sides of it for it to work. This doesn't matter for an E1 mechanism. 20. Draw the mechanism for the following reaction. We have tert butoxide attacking this 2-methyl 1-bromopropane, or 1-bromo 2-methylpropane, and it is merciful enough to like put the hydrogen there for you in the structure. And we've got tert butoxide. So what we get is attack on the hydrogen. This bond comes down, connects the 2 carbons, and this dislocates the bromine. My guess is with this one is it's probably much more of an issue of just kind of like getting the arrows in the right place. So I'm going to switch up, touching onto the desktop. So we're going to go from the oxygen to the hydrogen. The hydrogen bond, come on, to that bond. So basically just rotate the bond over, and then we're going to break the bromine carbon bond. And it thinks I did a great job. So yeah, usually the issues I see with those are more just like it's finicky about where it wants you to put the arrows. 21. Using curved arrow notation, draw the mechanism for the formation of the alkene formed. And they are obnoxiously using hydroxide because that's really not confusing. pH here is phenyl. It's basically just serving as a big bulky group. And it wants you to draw the mechanism to get to the alkene. So it's going to look a lot like the tert butoxide. I really wish they wouldn't use hydroxide. So this is going to attack the hydrogen. The bond here is going to come up, and we're going to break the bromine. So same idea as before. It's just trying to getting you to like work through that mechanism. All right, 22. This is a 2-part question. First, drawing the minor alkene product that should form based on the reaction. Second, draw a stepwise mechanism that allows the formation of the major product. So we're doing elimination under self-lysis. Okay. This is an odd little question. Let's see where it goes. 2 ways this can happen. So it already tells you this is the major product. The minor product, I'm going to guess, is the not Zaitsev product. So we can do elimination off of this hydrogen. So let's see what happens when we eliminate off of that hydrogen. Thought that was correct. All right, so it's just saying this is the anti-Zaitsev product. We're going to call it anti-Zaitsev since we got anti-Markovnikov. Let's do it anti-Zaitsev. Yeah, it's weird. It's like, because there's a couple ways this can go with methanol being in here. They could also do substitution. It's just a witch's brew. And so we're going to kind of cheat and use the context of the questions. We know that these are alkenes. All right, so when we heat, what do we expect to happen first? Well, we don't have a good base in this case, but we do have a decent leaving group, and we have a tertiary carbocation. So my first guess would be that we're going to dissociate to give ourselves bromide and this carbocation. Oh, and it wants you to draw the arrow. So we're going to do this by just breaking this bromine, carbon-bromine bond. All right, next step is that's correct. So first thing we do is we break it. This will be through an E1 pathway. Second step, we have a carbocation, hydrogen, and we have our methoxide. What will happen here is we have oxygen attack on the hydrogen. We'll break the hydrogen-carbon bond. This will come down, and we'll end up forming our desired alkene, as well as this hydronium-malate complex, so methonium, I guess. But it's our lone pairs and oxygen that will attack the hydrogen. Then hydrogen will break its carbon-oxygen bond. Those lone pairs will come down and they'll attack. We'll add that to give us our double bond. I always kind of wondered if like these are real reactions or people kind of make them up. Like I see these in textbooks and I'm like, I'm wondering if anybody actually does this. And that's it for that problem. That's all that happens is that we heat it up, that dissociates the complex to give you the carbocation, and then your methanol extracts the hydrogen, and that gives us the alkene. Draw a stepwise mechanism for the formation of a racemic mixture of both the RNS forms of this 4-methylcyclohexene. So this is going to be very similar to what we just did. So what we're doing is we're heating this in water. Now, what I find really interesting about this is that this implies that if you heat this up, you can generate, because this right now is a chiral molecule. Oh no. It does have stereochemistry though, so these are definitely cis-methyl iodo. And in principle, what this is claiming is that if you heat this up, what will happen is that the iodine will pop off. And you get this carbocation intermediate. So that also implies that if you have this cis mixture, you can turn it into a mixture of cis trans just by heating it up. And again, I kind of wonder if these reactions actually happen or just people like use these examples and don't know if they really happen. But anyway, I'll show you really quick on the desktop. You're going to break this carbon iodine bond just by heating it. And then this will leave you with now what water is going to do here in this mechanism is going to make you draw the water in, I guess, just to make you do it. And you're going to have to draw hydrogen too. Your water, the oxygen on water here is going to attack the hydrogen. This is going to break the bonds. And you're going to end up with a mixture of either plus H3O plus. And I'm sure it's going to be picky about whatever I just drew in there. All right, question 25. If it's just a demonstrated mechanism, it doesn't matter either way, would it? Yeah, but I mean, I just find that kind of fascinating is like, well, if this doesn't actually happen, I mean, someone's going to read that and come up with another example based on a false premise. Like, how far do these false premises go? Do we end up creating a whole set of examples that are wrong because, like, they historically were based on a bad example? Ooh, I remember this one. Draw the carbocation intermediates for the following reaction. And this is a big, nasty molecule, but it's honestly not as hard as it looks. So, I'm going to show you the molecule on the desktop. We'll work through this together. So, what you've got here is a carbocation rearrangement. So, what will happen is that we add the hydrogen. And please, oh, this was like a horrible one to draw. It's all coming back to me now. This would also be a lot easier if I had a mouse instead of like a trackpad. All right, so the first thing we're going to do is we're going to protonate that alcohol. How many steps is it going to give me? Hold on, I need to see how many steps it's going to get me to do this. So you add an H and you lose a water, and what that's going to generate is the first carbocation. Come on. So we get the first carbocation. Next thing we do is we get carbocation rearrangement. Be a nice problem if they like kind of gave you the structure to begin with instead of making you draw the whole thing out. Stupid trackpad. So we've got that there. I know it's daunting to watch me do this. So we get our initial carbocation, we get our carbocation rearrangement, and when it does rearrange, it puts it adjacent to a quaternary carbon, so there's no hydrogens to be eliminated, and that's how you get the final elimination to make that terminal alkene. So yeah, basically with that one, you protonate the alcohol, it pops off, you get carbocation rearrangement, and then you get that terminal alkene. All right, 26. Draw, ooh, so this one's going to follow the same complex. It's actually something I put in revised packets. I do like I think they're esoteric reactions, but they're nice illustrative reactions. So we've got this molecule and you heat it up. And so it says the first thing you do is you add H2SO4 and you lose water. All that means is that you're protonating this to get an H2O plus, and then it's going to disappear, and we get our carbocation. Now, what we get after this is just basically a methyl rearrangement. This bond here is going to move over, and we're going to end up generating this molecule here. So step one, we protonate, form the carbocation. We can get this methyl rearrangement. It's the same mechanism as the methyl rearrangement. It'll end up opening this 5-member ring and turning it into a second part of the 6-membered ring, and then we get elimination between the two, and that gives us the final alkene. 27. All right, draw the carbocation intermediates for the following reaction. So, bit of a nasty molecule. Mercifully, this one actually kind of gives you it pre-drawn. So I'll switch to that because it's a lot easier than drawing it on the board behind me. So first thing we do, that minus H2O, we're losing the alcohol to form a carbocation, which will go in that quarter. And we've got our two methyl groups. 2. That. So it looks just like this one over here, but we just popped off the OH group and given ourselves a carbocation. All right, rearrangement here. You can kind of infer it from the final structure, but if you didn't want to infer it from the final structure, if we move this carbon over, we don't really get anything for it. We take a secondary, convert it to a secondary. But if we take one of these methyl groups and put it over here, so we get a methyl shift, we take a secondary carbocation and we convert it to a tertiary carbocation. And so that's your two steps. First you form the carbocation, and then you get carbocation rearrangement. (34). The elimination of 5-bromononane on treatment with potassium methoxide is stereoselective. Select the correct Newman projection of 5-bromononane using the conformations that lead to cis-4-nonene and trans-4-nonene respectively. Identify the proton that is lost in each case by selecting the Newman projections that have the hydrogens colored blue. Subject the mechanistic explanation for the observed stereoselectivity. So let's start with the starting compound, 5-bromononane. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And 5-bromo. 1, 2, 3, 4, 5. So this is going to be the middle of the molecule. I'm just going to draw this out. It's symmetric, so it doesn't really matter. So the question is, how do we eliminate this in order to make the alkene? Well, we've got two hydrogens on the adjacent carbon. So if we were to eliminate like this, this would give us the trans isomer. In order to get the cis isomer, nine. In order to get the trans isomer or cis isomer, we need it to be kind of in this cis shape. So when we do the elimination, like the backbone doesn't move, right? Like it's all on the same plane. So when we eliminate this bromine, it needs to be, for this to be the trans conformation, it needs to be staggered. So if we draw a Newman projection of this, we've got the whole carbon chain, we've got the bromine here to the left, hydrogen to the right, and if we look behind it, we have the rest of the R chain, and we've got a hydrogen up and a hydrogen up. In order to get the cis conformation, again, if we look down this bond for the Newman projection, we've got our R group up, our bromine down to the right, hydrogen over. And if we look on the back side, in order for this to be a cis elimination, to form a cis product, what we need is this R group to also be up, and this is going to give us a hydrogen here and a hydrogen here. So let's look at the trans product. It wants to know what hydrogen is going to be eliminated in order to make this happen. So here it's really easy. In order to get the trans product, it's the hydrogen anti-periplanar to the bromine. So this one's pretty straightforward. This one there isn't one that is anti-periplanar. So what we need to do is we need to rotate this. Get everything gauche. And I rotated the wrong direction. And we have to rotate it until we get one hydrogen that is anti to the bromine. So again, in order to do the trans, what we need here is we need a hydrogen opposite of bromine. We naturally get that with the trans conformation. In order to get the cis conformation, we need everything gauche, and we need it gauche in such a way that the bromine is opposite the hydrogen. So let me switch it down to the desktop. So in order to get the cis, we need a bromine opposite of hydrogen. That's what we have here. And the hydrogen that's being eliminated is the one that's opposite the bromine. Oops, wrong one. So the blue hydrogen here has to be up, opposite the bromine. And that's how we're going to get the elimination where these two are on the same side. For the trans, the bromine and hydrogens have to be opposite. So the bromine and the hydrogen opposite. And we've got our alkene groups, the rest of the chain being anti. So it's going to be this top right one here. So the alkyl groups, so for the cis one, the alkyl groups move closer together, and the van der Waals strain increases while they do this. So I really wish the book actually, so we talk about why cis isomers are more stable. First of all, let me make sure this is right. Check my work. And it's all correct. So we talk about, come on, where's my mouse? We had a discussion board where we talked about where the cis isomers are less stable than the trans isomers, with the exception being cycloalkenes. And the answer, why, is sterics. There's also a great argument here is like, why mechanistically, why do we get two separate answers? This is actually a nice problem for demonstrating that in order, if you want to do a trans alkene, getting things anti-periplanar to make that work actually isn't that hard, because particularly if you have two hydrogens on the adjacent one, it's really easy to make that happen. The cis actually requires them to like come together, so you're climbing up an energy hill as you're starting to make this alkene. So I do like that problem. It's harder than anything you see on the test, but I do like that problem. 39. Predict the major product of the following reaction and draw the stepwise mechanism. So TSOH in this case is tosyl acid. So tosyl chloride we used before to make the OH group a good leaving group, and we use this for SN2 to drive an SN2 mechanism with alcohols. Tosyl hydroxide, or tosyl acid in this case, is going to be like sulfuric acid. So the major product on this is basically acid catalyzed dehydration. So you're going to get 1-methyl cyclohexane. So now it's going to ask you to go through the mechanism step by step. So I'll bring it up so you can see it step by step. So first thing we're gonna get is protonation of the alcohol. So that's going to take the hydrogen. And we're going to end up with this basically hydronium complex. And we're going to end up with the tosylate ion. Next up, we're just going to break that bond between the alcohol and the ring. End up with a carbocation. And water. And then the last step, our tosylate, because it is a weak acid, it's going to form a weak base when it gets done. It's going to go from the oxygen, attack the hydrogen, and we're going to end up with our finished product. Come on, connect. You're not going to have like TSOH as the like potential product. So that's the stepwise mechanism. It should look a lot like any acid catalyzed dehydration of an alcohol. All right, so that's 39. Next one is going to be 40. So this is the same one. It's got the TSOH. It's asking you what's going to happen. This is going to be the same situation where you protonate the alcohol. The alcohol is going to pop off. You're going to end up with, so the starting alcohol here. Basically your TSOH is just a hydrogen source. You're going to create that structure. It's going to break. And you're going to end up getting this carbocation, and this is going to subsequently eliminate with the TSO minus to give you the 2,3-dimethyl butene, 2-butene. But it's the same as 39. Like the only thing that TSOH here is just it's an acid source and a base source. So that's it for the questions I got emailed. So yeah, if you got questions up in the chat, please feel free to ask them. But that's about all I got. So you can see kind of earlier in the stream, somebody popped up with a comment on Teams, so I'm going to take a look at that. But I am here if you got any questions. Good to know that for tomorrow. Okay, so the hydroboration oxidation, is that sin? Yes. So if you do hydroboration oxidation, so we have all of those wonderful steps that go into it. What we're going to do is we're going to add the alcohol to that's not how I want to draw it. So if we do hydroboration oxidation of this, just as drawn, we would add an OH. But here the thing is that we created a chiral center here. So if we were to draw this from the stereochemistry standpoint, when you get done doing the hydroboration oxidation, what ends up happening is that the OH and the H are on the same side. So the nice thing here is you get a unique single product in this case. It'll push them up and down, so you'll get both the R and the S chiralities. But there is stereochemistry associated with it. It's just the hydrogen happens to be added to the same side as the OH. And if you drew that, you'd be correct. Typically, because we get both, you'll see some books draw that and say like it's both R and S. It has more implications when you do ring chemistry, so I guess that's why, that's more the point that needs to be driven home, is that, so if you have this compound here and you do hydroboration oxidation, the thing is that the alcohol and the hydrogen get added to the same side, so whatever you finish up with needs to be a trans complex. We have OR. So if we do hydroboration oxidation on this molecule, we will always end up with the trans 2-methylcyclohexanol. We will never end up with the cis 2-methylcyclohexanol. So I think ring chemistry is really more where the stereochemistry begins to show up and becomes very important. Study bracket 4. Do you have the page that you're looking at? I'm guessing it's page 11. Yep, it does give all 4. That might just be a typo in the key, honestly. Because, yeah, it should give you... Yeah, it's a typo in the key. So where it's got the two, what look like, we're going to call them cis. It's not really cis, but you'll know what I'm saying. The cis alcohol bromide, that's incorrect. So that's just a mistake in the key. Yeah, just in case you didn't catch it, yeah, I think the key's wrong. Only half of those should be up there. It happens. Got the chat up. You got any other questions? All right, so quick asked about allylic hydrogens. They are a unique category of hydrogens within a alkene. And they are unique because they are stabilized by the double bond. So these end up actually being easily removed by sheer merit of the fact that a lot of our mechanisms for removing them are resonance stabilized. So let's say we go through a free radical mechanism. So if we get rid of these hydrogens and we make it a radical, we can actually resonate that bond and get this structure. So because we have two resonance structures here, that's inherently more stable than just a radical by itself. And this includes even terminal radicals. So if you have a terminal radical, something that's on a primary carbon, that radical is more stabilized if it happens to be adjacent to a double bond. So if we put a radical here, that radical is inherently more stable than if we had the radical without the double bond. So this is going to have a lot of implications, particularly when we start looking at free radical halogenation. So this can be done with NBS and bromosuccinide, and the bromosuccinide is a very controllable way to add bromine. But from what I understand reading about it, it's really something that only works if you have allylic hydrogens because it's not that great at forming radicals. So let's say we had this molecule and we compared it to this molecule, and I said, okay, let's throw something down there to make it a little bit more complicated. So let's say I said we're going to do halogenation with light. Well, from test one material, we talked about how to do free radical halogenation, and what we want to do is you want to do it on the most substitute carbon. So if we didn't have a double bond, this would be the carbon that got the substitution if we did monobromination. But that changes if we have a double bond. So if we have a double bond, these two sites end up being the most likely site of substitution. So throwing this double bond in here changes where we can do substitution of the molecule because those allylic hydrogens are stabilized. Basically, a lot of the reaction intermediates are stabilized by that double bond. So I'm assuming that was your question about them. Basically, they are unique because they are this double bond. We have the option of a resonance arrow. And that resonance arrow gives us the ability to basically kind of, when you have resonance, basically all the carbons start sharing the burden of whatever the reaction intermediates are. No, you would just be told. So high temperature and low temperature here is kind of subjective, as is high concentration, low concentration. It depends on reaction conditions that will dictate what you get. So let's say we react with, we'll take a nice simple symmetric alkene and we react it with KMnO4. We're really going to get both products. So both of these are going to be present in the reaction mixture when we get done. But if we were to draw like we'll say this is blue and this is red, and we were to look at temperature or concentration, and we look at percent of the mixture. At low temperature, low concentration, this is going to dominate, and then as we start increasing the temperature, it's going to start getting less and less pronounced. The reverse is going to be true with the ketone in this case. As we start raising the temperatures, we start seeing this inversion. But you'll find temperatures where they're both kind of equally favored. You kind of have to go to one extreme or the other, and generally we just specify, and even then, it's one of those things that depends on a lot of other things as well, like how constant is this your solvent? If this isn't your solvent, the concentration of this is going to be low regardless, and so you're probably going to drive the diol. So yeah, the bigger thing here is it's kind of like when we talk about elimination versus substitution reactions, you're going to get a mixture. What you're trying to do is you're trying to favor the conditions that when you go to do the purification, this is a majority of what comes out, or this is a majority of what comes out. Then again, you wouldn't have to give a temperature. That would depend on what you're working with. You wouldn't have to give like, oh, it needs to be 1 molar, 2 molar, 3 molar. Probably with what you're working with in the lab, because you're working with such concentrated potassium permanganate, it's probably almost always forming the ketones, aldehydes. But other than that, I would say draw based on what you're being told. So you'll be told if it's low temperature, low concentration, or high temperature, high concentration. And that'll be the tip-off to make sure that you understand, if we're assessing your understanding, if you understand what that reaction does, you'll know when those conditions are specified what you should be getting. But you're not going to see something like 25 degrees C, you're going to see something like low temperature. You're not going to see something like 1.8 molar, you're going to see something like high concentration. So there's not going to be ambiguity here in terms of the reaction conditions. Yeah, you're welcome. You're welcome. And yeah, I'll stay on for a little bit longer. Right. So good enough for today. Again, if you ever have questions, these are not lectures, these are not lessons, these are office hours. So if you have questions, please feel free to email Advance. You can post in the chat, Advance. I will try to figure out what's going on. Honestly, I think I just forgot to like load, create a live stream for Monday this week. And so hopefully by the end of this week, I'll have those kind of worked out. Anyway, talk to y'all later.